Hello, and welcome to the Cosmic Adventures Lecture Series. I'm Dr. Mindy Townsend, the astronomer with Dudley at Siena. 2024 is going to be a big year because a solar eclipse will sweep across North America on April 8th, 2024. Everyone in the lower 48 states will experience at least a partial eclipse, and it's the last time that this will happen in the US for a couple of decades. So it's actually a pretty big deal. To get us ready for this rare event, I want to spend the first few lectures of the year talking about eclipse-related topics. If you were with me last month, you might remember our discussion of the sun, which is what is blotted out during a solar eclipse. This month, I'd like to bring the second celestial body that makes an eclipse happen into focus, and that is the moon. So as an astronomer, I am not supposed to like the moon. If your goal is to view things in the sky that are very faint, the full moon is actually kind of your enemy. The full moon is by far the brightest thing in the night sky, and the light it reflects overwhelms everything. But I actually do really like the moon. It's so big and so bright that it's almost tangible. How many other worlds can you just go outside and look at and see the surface? Looking at the moon through a telescope, you can see the contours of its cliffs and its craters. It's the only place in the universe, other than Earth, that human beings have actually set foot. Because the moon is so big and so bright and so close, humans have been looking at the moon and studying the moon for a very long time. So on your screen now, these are just the missions that landed on the moon through 2020. Humans have landed on the moon in some way 22 times. Only the Apollo missions put a human there, but like Mars, the moon has been explored with robots from the United States, the Soviet Union, and China. There are dozens and dozens and dozens of more missions, over 140 moon missions in all since the 1950s. The moon is one of those really incredible things that has been turned kind of mundane by familiarity. There's almost like a been there, done that attitude towards the moon. But my goal here is to convince you that there's actually nothing boring about Earth's closest neighbor. There are plenty of more questions to be answered. The moon is, in fact, extremely mysterious. So that brings us to our first moon mystery, which is water. Although we know that there are no large bodies of water on the moon, we do now know that there is water, but it has taken actually a very long time to come to that conclusion. The presence or absence of lunar water is kind of the mystery of the moon. Before we could send robots and people, all we could do was look at the moon from Earth. So all we could do for thousands of years is look at the moon from Earth. And what is one of the most obvious things about the moon, right? It might be these large, dark areas. Astronomers call these dark areas Maria, which is Latin for seas. Michel van Landeren published this map of the moon in 1645, actually labeling these dark regions Maria. We've been calling them that for a really long time. And you'll notice that these light areas are dubbed Terra, which is, of course, land. So we had kind of like a land-ocean dichotomy like we have on Earth. You can see how people might have thought that the moon had vast oceans. People centuries ago obviously didn't have the technology to see the Earth from space, but oceans of Earth do kind of appear like darker regions, right? Plus, hey, there's vast bodies of water on the Earth. Why not have vast bodies of water on the moon as well? Well, it turns out there are several reasons why vast bodies of water would not survive for long on the moon. Chief among them is the moon's lack of a thick protective atmosphere. Sunlight would really immediately vaporize any liquid water. We know now that these dark areas are actually plains of basalt, which is a rock that is a common product of volcanic eruptions, and yet the nomenclature still remains. This is how we get names like the Sea of Tranquility for the landing site of Apollo 11, the first human landing on the moon. So we kind of chugged along in this way for a couple hundred years. But then around the 1890s, an astronomer called William Pickering was able to make measurements of the moon's atmosphere by using a phenomenon called occultation. Occultation is when a foreground object, so in Pickering's case, the moon, passes between him and a background object. So in Pickering's case, that is Saturn and Jupiter. So this is an example on your screen here of a lunar occultation of Saturn taken in 2014. So the lunar atmosphere is extremely thin, but it is there. Pickering could make measurements of Saturn and Jupiter as it was passing behind the moon, and from those could make some determinations about the moon's atmosphere. He calculated that the atmospheric pressure on the moon is so low that ice would quickly vaporize. It was because of these calculations and observations that for the next 70 years or so, the astronomy community mostly accepted that the moon was bone dry. In the 1960s, though, scientists started to rethink their assumptions. In 1961, a team of theoretical physicists published a paper arguing that it is not impossible for water to exist on the moon in the form of ice. The trick is that the water ice would need to be in what astronomers now call permanently shadowed regions, like at the bottom of large craters, for example. These places never see the sun and can thus stay frozen. So this paper just argued that water ice is possible on the moon. These were theoretical physicists. They weren't making any observations, so they didn't know for sure. Measurements in those permanently shadowed regions were necessary to say one way or the other. Luckily, in the 1960s, we started sending lunar orbiters, or robots sent to orbit the moon and take pictures. We started getting back some of the best images of the moon we'd gotten to date, and they showed some features on the surface that looked kind of like riverbeds, or this reel right here, or filled in or flooded craters. So this is a photo showing these features from the Lunar Orbiter 5, which was launched in 1967. So these features could have been produced by running water sometime in the moon's past, or they could have been created by volcanic activity on the lunar surface. So these are two very different processes that we really can't tell the difference between from pictures alone. So people really started asking, is the moon as dry as we think it is? The idea that those supposed riverbeds or craters could have been caused by water was thoroughly disproven when we started actually landing people on the moon. It became extremely clear that those formations were caused by volcanic activity, not water. But that doesn't mean that the question of water on the moon was settled. Thanks to the Apollo missions, we actually had samples of lunar rock we could analyze in our labs on Earth. The story these samples told was a story of a brutally dry lunar surface. Analysis of the lunar rocks showed that there were only a few parts per billion of water, and instruments like the Lunar Atmospheric Composition Experiment were left to measure water in the lunar atmosphere, and it showed that the atmosphere was about 1% water, which was barely detectable by the instrument. In addition, the dearth of all other volatile substances on the moon's surface, or substances that have very low melting points, like dry ice, for example, indicated that water would also be in short supply. So, seemingly confirmed by hard data was this idea that there's basically no water on the moon. I do want to note, however, that during this time, there was actually some evidence for water in the interior of the moon. Luna 24 was the last in the Luna series of missions to the moon by the Soviet Union. This mission in particular brought back samples from Mare Crisium that were, as far as we know, uncontaminated. What scientists found when they analyzed the sample kind of flew in the face of the Apollo results. They found definitive evidence of water in Mare Crisium. Analysis showed 0.1% water by mass, which doesn't sound like a lot, but it's more than what the Apollo analysis was finding. In addition, the water signal got stronger with depth, meaning that there was more water the deeper into the lunar crust you went. So this finding was essentially ignored at the time, but I think it's good to know because it provides some nice foreshadowing of what is to come. Okay, so despite the Luna 24 samples that everyone for some reason ignored, for the next 30 years or so, most credible scientists accepted that the moon was dry. In the mid and late 1990s, two lunar missions again started to change our thinking on lunar water. The first was Clementine, launched in 1994 to make scientific observations of the moon. One of its missions was to use bistatic radar technology to look for water ice on the lunar north and south poles. This experiment made observations that were consistent with an icy surface in permanently shadowed regions of the lunar south pole, rather than a rocky surface that you would expect if there was no water ice, but the results were actually kind of inconclusive. In 1998, the Lunar Prospector mission was launched. This was another orbiter that was tasked with mapping hydrogen deposits on the lunar surface, measuring the moon's magnetic and gravity fields, and measure lunar outgassing events. Lunar Prospector kind of added more gas to the fire, so to speak, by finding large hydrogen deposits at the north and south poles. However, it was unclear whether this was a sign of water or a sign of something called a hydroxyl radical, which is basically a molecule made with one oxygen atom and one hydrogen atom instead of two like water. When its mission was completed, Lunar Prospector was crashed into the south pole of the moon so we could kind of observe what debris it kicked up. We really wanted it to kick up some water ice, but unfortunately, none was found. So here we are actually coming up on the year 2000, and we're still having a hard time conclusively finding water on the moon. The signs are there, but we really can't say for sure. So jump ahead 10 more years to 2008. The Indian lunar orbiter Chandrayaan-1 launched in October of that year. This was India's first lunar mission, and it turned out to be a doozy. The goal was to study the moon's geology on a molecular level, to study the chemical and mineral composition of the lunar surface, especially the permanently shadowed regions around the North and South poles. Among its onboard instruments was the M3, the Moon Mineralogy Mapper, designed to map the surface mineral composition. What they found was signs of hydration across the lunar surface. So this is a sign of water, but not water itself. When scientists say they found evidence of hydration, that means that they found evidence of a chemical reaction that happens when a different substance combines with water. These signatures were found in sunlit regions of the moon, not the permanently shadowed regions, which is also an incredibly intriguing result. So on your screen now, this is an image of um, well, something we got from M3, the same region of the moon shown side by side. The blue is where there is evidence of hydration, and this evidence is all over the sunlit region. At the same time as all this was happening, scientists on the ground were revisiting Apollo samples, and this time they were actually not coming up empty. Initial analyses of the water content in the lunar samples found that the amount of water on the moon was about 1 part per billion. So that is extremely dry. One reason we thought that is because moon water looks a lot like Earth water. So when scientists take samples from anywhere, there is a concern about contamination. So we need to be especially careful when we get samples from space because our sample containers come from Earth and microbes and skin cells and sweat are absolutely everywhere. We don't want any of our Earth gunk getting into our pristine outer space samples. Otherwise, how can we know if we found life on Mars or just a piece of a dead microbe that is very common on Earth? Also, we don't want to accidentally seed another planet with life by accident. We want to really preserve what's there. So we're generally extremely careful with what we send into space. Everything from satellites and telescopes to orbiters and landers are kept in clean rooms until it's time to move them to the launch pad. The problem with the Apollo samples is that this didn't quite work as intended. The containers the Apollo crew used to store lunar samples didn't seal properly. Lunar dust, it turns out, is incredibly rough and jagged, and it sticks to absolutely everything. And that dust clung to the containers in such a way that their seal wasn't as tight as we would like them to be. So why does this matter? If we found water, we found water, right? It's not quite so simple. I mentioned how the water in the lunar samples looks like Earth water. And here's kind of what I meant by that. Scientists can tell where certain substances are from based on what isotopes that substance has. So I want to pause here and briefly discuss what an isotope is, because understanding a little chemistry is actually kind of important when studying the moon and the planets. So an isotope is an atom that's basically with extra neutrons. Like simply put, atoms are made of basically three different things, right? Protons and neutrons in the nucleus and electrons swarming around the nucleus. Protons are positively charged, electrons are negatively charged, and neutrons are neutral. So you might be familiar with the periodic table of elements that's on your screen right now. It's a graphical representation of this idea that chemical properties have a dependence on an element's atomic number or a dependence on how many protons an element has. Normal atoms are neutral, meaning that typically the number of protons equals the number of electrons. So take the element oxygen, for example. It's pulled up here at the top of your screen. Its atomic number is 8, meaning that it has 8 protons and 8 electrons. The number of neutrons a given element has is a little bit more tricky. For example, most oxygen atoms have 8 protons, 8 electrons, and 8 neutrons. If all oxygen atoms had this configuration, oxygen's atomic weight or atomic mass would be 16. But you'll notice it's not 16, it's 15.999. That's because while 99.8% of oxygen atoms have 8 neutrons, the remaining 0.2% have between 3 and 18 neutrons. The variation in the number of neutrons doesn't change the element, it just changes what isotope the element is. Molecules like water can have isotopes as well. That just means that the molecule composed of 2 hydrogen atoms and 1 oxygen atom can have some combination of different hydrogen and oxygen isotopes. It's all still water, but the elements it's made out of are a little heavier or a little lighter than what we would typically see. So this is just a cartoon of various water isotopes. So on the far left is what I'll just call normal water with a total mass of 18. The other cartoon water molecules are a little bit heavier because they include heavier versions of hydrogen or oxygen. They're still water though. So the ratio of normal water to water isotopes is expected to be different on different planets and moons because no two objects have the exact same formation history. Just like two people can come from the same family and turn out differently, there are big similarities, but we can distinguish the subtle details. So this is what happened with lunar water. The isotope ratios, the amount of water isotopes compared to regular water in the Apollo samples were virtually the same as the water isotope ratios we found on Earth. And since scientists knew that the containers didn't seal properly, the assumption was that the water they found was just Earth water that had contaminated the sample. But hey, we're starting to get some interesting data. The Clementine and Lunar Prospector missions gave us a sliver of hope that maybe we just weren't searching quite hard enough and that there was water on the moon after all. Technology has also advanced a lot since the 1970s, and in 2008, a team at Brown University revisited the question of lunar water by studying the Apollo samples with modern methods. Using these methods, scientists found evidence of water inside lunar volcanic glass. Because water was found inside the glass, this indicates that the water's origin is not Earth, but instead comes from beneath the moon's crust. In addition, new analysis methods allowed for a more nuanced look at the composition of lunar rocks. In the 1970s, to study what a rock was made of, you basically had to vaporize your sample. That means that you could measure how much of an element was in the rock, but you couldn't tell if that element was concentrated in one area of the rock or if it was more evenly spread out. New methods allowed scientists to preserve the spatial information. They could identify where the element or mineral or molecule was in the individual rock. And they found that there was actually more water towards the center of volcanic glass beads as compared to the edges, indicating that the water they found was of lunar origin, not Earth. So this is a plot from one of their papers. You have the center of the rock over here towards the edge, and their data clearly shows a trend of more water towards the center, less water towards the edge of the sample. So now we're really starting to get somewhere. All of the ambiguous evidence of water is starting to lean to one side, and more evidence of water is to come. In 2009, the Lunar Crater Observation and Sensing Satellite, or LCROSS, and the Lunar Reconnaissance Orbiter, or the LRO, launched with the goal of studying the nature of hydrogen on the moon and to further study lunar water. These are both robot orbiters, so they didn't make soft landings on the moon, but they did throw stuff into it. So LCROSS shot a projectile into the Cabeus crater near the lunar south pole, indicated with the blue circle, a crater where there was believed to be water ice, so it would kick up a lot of dust and debris. Then LCROSS flew through the dust cloud and measured its contents. It then threw itself into the moon and crashed into the lunar surface while the Lunar Reconnaissance Orbiter watched. So this is a map of the lunar South Pole from the LRO, from the Lunar Reconnaissance Orbiter. The colors represent temperature, with the blue-purple regions being the coldest. So to look for water ice, we're really interested in kind of the coldest parts, so those blue-purple regions. For its impact, we aimed LCROSS for that star right there, right here on your screen, which is one of the coldest regions, in hopes that it would kick up some water ice. So this is kind of what the debris looked like from the LRO. LCROSS shot a projectile and crash-landed into the Cabeus crater, which is in a permanent shadow, and by doing so, it kicked up rock and dust into the light so we could more easily see what was hiding there. But what did these measurements find? Did LCROSS die in vain? Well, both of these measurements indicated the existence of pure water ice. So that is a result. Pure water ice in permanently shadowed regions of the moon. But we're not done yet. Remember Chandrayaan-1 and M3? So the satellite stopped operating in 2009, but it sent back so much data that scientists spent the next decade studying it. Specifically, the Moon Mineralogy Mapper gave us the first high-resolution map of the minerals that make up the lunar surface. So M3 made this kind of psychedelic map of lunar minerals, but the important regions for us are really kind of right here. These blue and purple regions at the lunar north and south poles. Each color on here represents a wavelength of light detected by M3. The blue is about 3 microns, which is an absorption line for water. As you can see, water is highly concentrated at the poles. These regions, though, don't get much sun. In fact, the green on this map represents the heat being released after being heated by the sun. The North and South poles don't have a lot of green there. So the water in cold and shadowed regions confirmed. We want to know if water also exists in the warmer, sunlit regions of the moon. Confirmation of water in sunlit regions of the moon came in 2020 using data from the Strategic Observatory for Infrared Astronomy, or SOFIA. SOFIA is an extremely interesting telescope. It's a telescope mounted in an airplane. Oh, it's right in this hole right here, mounted in the airplane, and it flies as high as we can so we have less atmosphere to get in the way. One of the reasons space-based telescopes like Hubble are so popular is because you can make observations without any distortions from the Earth's atmosphere. Sophia could fly high enough to avoid 99% of the water vapor in the atmosphere, which makes it a good telescope to look for things like lunar water. Sophia looked at the Clavius crater in the moon's southern hemisphere. It's a sunlit region. Previous observations indicated that there could be water there, but scientists couldn't distinguish between water, H2O, and something called that hydroxyl radical that we talked about earlier. However, Sophia actually could distinguish between these two extremely similar molecules and confirmed for the first time the existence of water in sunlit areas of the moon. So how is this possible? It was thought for a long time that water in these regions was improbable because water would be vaporized immediately by the sun without a protective atmosphere. The team that made this discovery hypothesizes that the water they're detecting exists in voids between the dust grains or inside volcanic glass, which would protect them from the harsh lunar environment. Sophia determined that there's the equivalent of a 12-ounce bottle of water per cubic meter of soil on the moon. There are concentrations between 100 and 412 parts per million, which is still dry, but it's way more than the 1 part per billion we thought was there in the early 2000s. Sophia has been decommissioned as a telescope, but data from its observations were used just last year to make the first detailed wide area map of water distribution on the moon. The map, a portion of which is on your screen here, covers about a quarter of the Earth-facing side of the moon in the lunar southern hemisphere. Its range extends to the South Pole, but a lot of this region is sunlit, further confirming the existence of water on the moon. Next year, NASA will send a new robot to the moon, the Volatiles Investigating Polar Exploration Rover, or VIPER, and it will further explore the lunar South Pole region and look for water and other resources that can aid future missions to the moon. It's scheduled to be launched, I think, late next year, maybe late this year. So I think as inhabitants of Earth, we have kind of ideas of what a moon should be. And as the discussion of water illustrates, that can kind of change over time. But there are some things that I feel we kind of hold dear, right? Like planets have moons, right? Earth's moon hangs very heavy in the sky, and it's often the brightest thing in the nighttime sky. It is so normal. But actually, our moon is very not normal, not in this solar system anyway. So on your screen here are some of the moons in the solar system, and everything on this slide is to scale. So you might notice that Mercury and Venus are not represented because they have no moons. Kuiper Belt objects, so the region of icy oddballs out beyond Neptune, Pluto and Eris actually do each have at least one moon. Even asteroids have moons. It's not just planets that get moons. So these are the largest moons around planets and other objects in our solar system. In general, kind of the biggest moons are around the biggest planets, right? The Galilean moons of Jupiter, so Io, Europa, Ganymede, and Callisto, they are very large. Saturn and Neptune also have quite large moons. Saturn has Titan, Neptune has Triton. Look at the size comparison with Earth's moon. With Earth's moon over here. And remember, everything is to scale. Earth's moon is also quite large. It's in the top 5 largest moons in the entire solar system. And there are hundreds of moons in the solar system. It's not just how big the moon is, it's also the moon's size relative to Earth. In general, the biggest moons orbit the biggest planets, right? Jupiter, Saturn, Neptune's are all gas giants with quite large moons. The Earth is not a gas giant. Think about this. Jupiter is 26 times bigger than its biggest moon, Ganymede. Saturn is 22 times bigger than its biggest moon, Titan. Neptune is 18 times bigger than its biggest moon, Triton. But the Earth is only 4 times the size of the moon. And so that's kind of it's a little bit strange. Like why would the Earth, which is so small, have such a large moon? It's just a little odd. Why this moon is this way, like why we have such a large moon, is itself quite a mystery. How our moon was made is itself a very large mystery. And we can start to untangle this by kind of asking a deceptively simple question. What is the moon actually made of? And the answer to that is the moon is made of Earth. Kind of, maybe. It's actually a really, really hard question, and it depends on what you mean by Earth. So on your screen now, this is a 4-pound moon rock brought back in 1972 from the Apollo 16 mission. It's mostly something called plagioclase, which is a rock that is formed from molten magma. And for the most part, this is what the lunar crust is made of. This rock is not very dense. It's the kind of rock that would rise to the surface of a magma ocean. And what this points to is actually a very violent beginning for our moon. Because really, here's the truth. There's a lot we don't know or understand about how the moon formed. There are different hypotheses, but the one that explains the most of what we see is called the giant impact hypothesis. This hypothesis states that 4.5 billion years ago, very early in the solar system's history, a Mars-sized object dubbed Theia slams into a young Earth. This impact threw a bunch of debris into space and eventually coalesced into what we now call the moon. This hypothesis explains a number of geologic observations we've made of the moon. This hypothesis also explains the moon's large mass, its angular momentum, its small iron core. But there are some problems. In particular, the mantles of both the moon and the Earth are surprisingly similar, way more similar than we think they should be if the moon was created by an impactor. If the giant impact hypothesis, the moon should be made of mostly impactor material. The moon should be mostly Theia, but it's actually not clear that it is. Planets and stars form out of clouds of gas and dust. As the star collapses and starts the process of nuclear fusion, the rest of the gas and dust that didn't make it into the star will coalesce into small planetesimals, and if conditions are right, will form a planet or two. Planets and their stars are extremely intertwined. Even so, each planet has a unique signature, like a fingerprint. The abundance of different elements are different on different planets, and the odds of any planet having the same elemental abundances of any other is actually quite small. To test the elemental abundance of different samples, geologists and planetary scientists will look at the abundance of different isotopes. So we talked about isotopes in reference to lunar water, and they come into play again in a big way here as well. If the moon was formed by a giant impact, we should be able to see the leftovers of that impact in the composition of the moon. And because we don't expect Theia and the Earth to have identical compositions, we expect to see differences in the composition of Earth and the moon. And this is where things start to get a little bit weird. So I'm going to show you several plots and I'll try to walk through them slowly, but this is an example of a review paper from 2020. And part of what this team did was gather a bunch of data from the literature and compare the amount of certain isotopes we find on Earth to those found on a variety of other solar system objects. The expectation is that there will be slight differences. So this is part of a plot from that paper comparing the difference in the abundance of isotope oxygen-17 to for a bunch of different objects. The vertical axis here is the measure of the difference in the oxygen-17 abundance of the different objects, which are all labeled across the top, as compared to Earth. So this line here, this is Earth's baseline. It is by definition 0, and we're measuring oxygen-17 abundance relative to Earth. If it's above the line, that means there's more oxygen-17 than you would find on Earth. If it's below, that means there's less. Okay, so look at this. Down here, we have a comparison between the Earth and the moon. Remember, the Earth is this baseline, black line right here. The moon is at the end, and its measurement is actually kind of bang on the line, has the exact amount of oxygen-17 as the Earth does. And it's not the only one. The same is true when we make a measurement for titanium-50, really kind of just bang on the line. The same is true for chromium-54. It's a little bit elevated, but it's within the error bars. So we'll say it's basically consistent with what we find on Earth. So, so this could happen. This all could line up. It is possible. It's possible that Theia had a very similar abundance as Earth, but it's just not very likely. So these abundances, they're a bit of a problem for the giant impact hypothesis because our modeling of moon formation shows that if a violent collision formed the moon would have the moon would have taken on 70 to 90% of the impactor of Theia. But we also expect Theia to have a different composition than the proto-Earth. And from what we can tell, Earth and the moon have basically the same composition. Or at least that's what we could tell until very recently. So planetary scientists, planetary geologists have been busy trying to reconcile this discrepancy. How can a hypothesis that explains so much and makes so much sense have this type of glaring inconsistency? For oxygen isotopes, at least, there may not actually be much of an inconsistency. The Apollo missions brought back a variety of lunar samples, rocks from different depths, soil, etc. What is usually done is that these are tested and averaged, the thought being that this gives us an average of the abundances of the moon as a whole. But what this team realized is that the different types of samples have different oxygen abundances. In a giant impact, a lot of the young proto-Earth would have been vaporized. Some of that would condense and fall back to form the Earth we know today, and some of it would condense and form the moon. This is what we call light vapor contamination. If the goal is to find Theia in the moon, we don't want a lot of this contamination. Certain types of samples are more susceptible to that type of contamination than others, so that's a pretty good reason to split up the lunar samples by type. And so we have a plot from their paper here. Vertical axis, again, is the difference in the oxygen-17 abundance. The red box on the far left, that is Earth. That is measurements for Earth. The colored boxes on the right are measurements from different types of lunar samples. The further right you go, the more contamination from vapor we think there is. So the green and orange boxes in the middle are the samples with the lowest contamination, and they show the greatest difference from the measurements from Earth. So what this plot is saying is that Theia might actually be there. We just have to look much more carefully than we've been looking so far. So I'm not a geologist, and I want to emphasize this as one paper, but it's a very intriguing result. It could be that we've just been averaging away Theia for all of these years. One of the issues, of course, is that we don't have an unlimited supply of lunar samples to test. To know for sure what's going on, we need samples really from all over the moon, not just a limited number of Apollo landing sites. More recently, geologists and planetary scientists have been investigating parts of the interior of the Earth that could be remnants of Theia. The interior of the present-day Earth is mostly comprised of three layers, and I'll make every geologist mad at me, but three layers: the crust, the mantle, and the core. This is caused by a process called differentiation, where heavier elements and molecules sink to the bottom. This is why Earth has like an iron core, right? It's heavy. But there are still stub layers and anomalies. Some of those anomalies in the mantle are known as LLVPs, or large low velocity provinces. They're called this because they slow certain types of waves that flow through the Earth. The Earth has a couple of these areas deep down in the lower mantle, just outside the core, and it's not really understood how they got there. These regions are enough different from the surrounding Earth to actually be pretty perplexing. They're more dense than the surrounding materials, and they have iron oxide content that we usually find on the moon. So could this be Theia? It may be, right? A team of planetary geologists published the results of some modeling they did, and they found that it is actually completely possible for a Mars-sized object to collide with Earth, and for some of that object's mantle to solidify and sink to the bottom of the mantle of the young proto-Earth, and for other bits of the Mars-sized object to actually be flung into space and form the moon. So basically, what they posit happened is that Theia and the proto-Earth collided and became completely molten. As Earth differentiated and solidified, there are small bits of Theia's mantle that could have solidified and sank to the bottom of the mantle, forming the LLVPs we see today. I want to emphasize the could here. So much of astronomy is trying to piece together things that happened a long time ago, using models that integrate the laws of physics and what we see presently helps us figure out if the ideas we have to explain what we see are even possible. It's not necessarily a smoking gun, And many geologists still are not convinced that the giant impact hypothesis is correct. But it's something that is being taken seriously as a formation model and something that scientists are still looking into. So I hope I've convinced you that the moon is actually far from boring. It holds the secrets to our early solar system. It's a laboratory and a launch pad for future crewed interplanetary missions. The moon is in many ways just our key to the rest of the solar system, and I, for one, am looking forward to what we continue to find there. So I want to put this map up. This is, of course, part of the eclipse series I'm doing the first few months of this year. I'm based in New York State, so I'm using a New York State map just to let you gauge for yourself where totality is in re respect to you. You will not see a total solar eclipse if you are kind of south of this dark line here. But if you are up here around Buffalo, Rochester, Syracuse, in the Adirondack region, North Country, you're definitely kind of in for a show on April 8th. I'm encouraging people to travel, but if you cannot travel, which I understand is not an option for a lot of people, um, cities and libraries throughout the state are doing their own eclipse events. If you look around where you live, even if you're outside the path of totality, I'm sure you will be able to find some people to share the day with. I sort of think that solar eclipses are kind of simultaneously one of the least accessible big astronomical events and the most accessible, right? Only a few people will be in the path of totality. It's a very small strip around the globe. But when it's happening, you don't really need anything special to experience it. You could have eclipse glasses, but you can also make a pinhole viewer. There's many different ways to view the eclipse, and I hope that you are able to do this wherever you are. That is all for me right now for the moon and for evangelizing for the eclipse. But hopefully, I will see you next month. We will actually dig into some eclipse science, some old lore of eclipses, and how you can actually view it safely yourself. So I hope to see you for that. Thanks.